So MML is experiencing issues. It was down yesterday for sure.
It's down now too.
Yeah, and it's their servers there's something wrong with their servers. It's probably not anything on your end that you're doing. So I don't have an ETA. They don't really communicate with us. So, we just have to check back periodically. Sorry for, it's frustrating, trying to do your homework and you can't even access it. So it's usually not an issue. It's, seamless through the semester in most cases. But every now and then something like this will happen, which is, again, another reason, like, if you can, stay up with the homework, just so this doesn't happen, like, the day before the exam and you're trying to get your homework done. So, it's really not of my control, but I do apologize. I know it's frustrating. Calculators should be in radians. So if your calculator's in degrees, you need to change that. We never use degrees in this class. Everything we input will be radians. So make sure you have your radian mode on. Are there any questions on the homework? Okay, so we did get through most of 2.1. We were discussing this, maybe, I don't know, shorthand way to compute this. So the exercise we did before, we just had a bunch of different time intervals, and we just computed this thing here for each individual time interval and came up with a particular number, and then that number represented an average velocity. And so we started talking about, well, what if I looked at an interval of 1 to 1 plus h? Because what I see here is I see intervals like 1 to 2, 1 to 1.00, etc. I've got this left endpoint fixed, and what I'm doing is I'm getting closer and closer to 1 for these right endpoints, 2, then 1.001, etc. So is there a different way to think about it? That's what this problem in your homework is going to have you do. Instead of saying it's 2, it's 1.001, let's call all of those points that are away from 1 plus h, where h just indicates the distance you are from 1. Okay, and when you compute this s of 1 plus h minus s of 1 over 1 plus h minus 1, again, that's the average rate of change. So this, or the average velocity. So this is the average velocity on the time interval 1 to 1 plus h. Instead of finding a specific number like 49.6 or whatever and saying that's the average velocity on the time interval from 1 to 2, we now have a general way to describe the average velocity on any interval as long as we're some distance away from 1. Does that make sense? So you're going to get a function of h. You have to, before you get the function of h, you need to simplify this. Okay. And for argument's sake, I'm just going to make something up. This has, nothing to do with this particular example at all. It's just, let's just say that we ended up with this average velocity function of h as like 2h plus 3. Then, instead of computing the individual average rates of change here, what we can do is say, well, what is h? It's equal to 1. So on this interval, when h is 1, all I have to do is plug it into this function. Okay. When h is 0.0001, then I'll just plug it into this function. And each time that'll give me the same average rate of change as if I were to go through those individually, like we did in the previous example. Okay, so that's the purpose of that exercise. Does anyone have any questions about that? So I'll just put 1 here, the average velocity on 1 to 2. H is equal to 1. And again, I totally made this 2h plus 3 function up. So it's, in a sense, it's an easier function to work with as opposed to finding like s of 2 minus s of 1 over 2 minus 1, then s of 1.001 minus s of 1. Okay. But either way, you're doing the same thing. It's just a different way to look at it. Okay. So if there aren't any further questions, then we'll end 2-1 there. Yeah.
There's only if h equals 1, right? That's
Yeah.
when we apply this.
Right. Yeah. So on the, like for instance, on the next one from 1 to 1 point, what is it, 001? If we're wanting the average velocity on that interval, then we got to plug in that h is 0.001.
So we can use that same equation. It's just a shortcut to the.
Yeah.
Okay.
Right.
Thank you.
You're welcome. Any other questions? Yeah.
It's off the subject, but
Okay.
are you recording?
Yes.
Okay, cool. I just don't see the little doodad. Okay, cool.
Yeah. All right. Save that. Okay. On to 2-2. Just making sure everything. Sometimes it's blank. So here we end up with a preliminary definition of a limit. Let me just back up for a moment. This figure here will sort of illustrate what we were doing. So remember, the idea of a limit in the context we've seen it in is to just make something closer to something else. That's all the limit did for us. It depends on what context the limit is inserted into. So when we take the slopes, or the average rate of change, and then we insert a limit into that, that will give us the instantaneous rate of change. And so visually what we were doing, we were working with these green lines. Here's the secant line. What's the slope of the green line? And we said, all right, well, we're going to fix this 1 point here at t equal to 1. And then we're going to make this right endpoint just get closer and closer to that, all the while looking at the slope of that green line, until eventually we get close enough to the fixed point where we have a very accurate value for the slope at a single point. Okay. So what you're seeing unfold is the process of a limit. What we're calculating, it varies from problem to problem, but that is a good visual representation of a limit as we've seen it so far. Yeah.
Could I just get one of those handouts that you had at the beginning?
From 2-2?
Yeah.
Yeah. Does anyone need another handout for 2-2, or does anyone need a schedule and a syllabus page? Yeah. All right. So there we'll end 2-1 there. And in 2-2 we get a preliminary definition of a limit, and it's not until 2-7 till we see the actual definition of a limit. So right now we're gonna just take this and get familiar with it. Look at limits visually, numerically, and see why that's limiting to do so. And then in 2.3 we'll start talking about ways to compute limits. So when we start getting to actually compute limits, it's all an algebraic process. So you've got to remember, do you remember in pre-calc where you had to find the difference quotient? It said find and simplify the difference quotient. Okay, so you've got to remember how to simplify functions like that, because a lot of those processes of simplifying are very prevalent when we compute limits. So the initial definition of a limit is we're going to say that we've got some function that's defined at all x near a, and a is just another x value. So we have a function that's defined everywhere except possibly at 1 or 2 or 3 different points. And f of x is arbitrarily close to L. So what we have to take from that is this L here is a function value. L is a y value. A is an x value. Okay. So if your y values are arbitrarily close to L, and that's just some finite number, L is some finite y value or function value. So if we're arbitrarily close to a y value, and it says as close as we like, and again it's ambiguous. The term's arbitrarily close and sufficiently close, but we don't make that precise until the end of chapter 2. So and just visualize that the y values are like honing in onto this finite number that we're calling L for all x values that are super, super close to A, but not equal to A. Okay. So that's, as we'll see, there's a big difference between just evaluating a function. Like if I say f of x is x squared, evaluate f of 0. There's a huge difference between just evaluating a function at a particular number versus calculating a limit on the function itself. Because when we calculate function values, we just plug those directly into the function. But what this is saying is that these are all x values that are really close, but not equal to that particular A.
Isn't that
So-
what arbitrary means too?
Do what?
Isn't that kind of what arbitrary means too, like close but not exact?
Yeah, arbitrary just means it's not specified, right? Like, are you this close? Are you this close? Are you this close? It doesn't specify how close. You know, what does it mean to be close, right? So it's just not specified. So if that's the situation that's occurring, we write this symbol here, and this is read as the limit as x approaches A on f of x is equal to L. So that's what that statement means. That's how we're going to denote our limits. The y value of the limit itself, L, if it even exists, depends on the values near A, not at A. Okay. So is that okay? Does anyone have any questions on that? The main takeaway here is that limits don't care what's happening at the function, or on the function rather, at A. Limits are only concerned with what's happening as we get closer and closer to something. So we'll look at some limits graphically. So figure 2.7, let's compute, find a few things here. Let's calculate, excuse me, f of 1. So what is f evaluated at 1? 2. F of 1 equals 2. Okay. Hopefully we're all familiar with that. Then we'll calculate the limit as x approaches 1 on that function, f of x. So the way we have to interpret that is, as I get closer and closer to 1 as an x value, what are the function values getting closer and closer to? 2. And since we're asking about what are the function values getting closer and closer to, visualizing limits like this, just imagine that the function itself is the road, and you have to travel along the road to get to this location. So x is approaching 1. So we have to travel to this location on the function. So maybe we're envisioning traveling this way or this way. So as x approaches 1 along this path, the y values get closer and closer to 2. Are there any questions on that? So again, the difference is, as opposed to evaluating a function, you just say, what is this value? When you compute a limit, you're just asking yourself, what is it getting closer and closer to? I don't care what it's equal to, just what is it approaching? Okay. What about evaluating f of 2? F of 2 equals to 5. Does everybody agree? Okay.
No, it shouldn't be 3.
Yeah, so should it be 3?
No,
No. Yeah, so is the function actually defined right here at x equal to 2? No, that point has been deleted. But there is a solid point here at x equals to 2, and that value is 5. So it is 5.
That is only when there is not a when there is a defined, undefined point.
Yeah.
Right, pretty much. So you have to look at the next best thing in reality. I mean,
Yeah, I guess that's a way of putting it, sure.
So what is the limit as x approaches 2?
Okay, so that's what we're going to ask now. What is the limit as x approaches 2 on this function? Okay, I heard 3. What do y'all think? So remember, the limit doesn't care about the function value. It just says, as we get closer, as x gets closer and closer to 2, what do my function values get closer and closer to? Right? So I'm not saying what is it equal to, I'm asking what is it getting closer to? So here's x equal to 2. Remember, the function is the only road I have to travel on, so I have to travel along this function until I get to that particular spot. But either way, the y values are getting closer to 3. No matter what direction you travel, the y values are getting closer to 3. Right? Like this would be, from the left would be 2.9, then 2.99, 9999, etc. Then 3 point up here from the right would be 3.01, 3.001, 3.0001, right? So does that make sense? That's really kind of the main thing to grasp about limits is just that notion there. Questions?
So f equals, or x equals 3, but there just be no solution. At f equals 3.
Okay.
X equals 3.
Yeah. So we're looking at that. What is f evaluated at 3? It's undefined. Notice there is no solid point above or below at x equals to 3. So f of 3 is does not exist. Undefined, however you want to say that. Can we compute the limit as x approaches 3 on f of x? Yeah, what would the limit be?
4.
4? Does everybody agree? The limit as x approaches 3 is equal to 4? Okay. Because as x gets closer and closer to 3, the y values get closer and closer to 4. So writing the equal sign is a bit misleading at first because at this point we're used to seeing equal sign meaning is, like this thing is, and that's totally true, but the nature of a limit, even in the very definition, is saying it's not equal to. X isn't actually, x isn't actually 3 in this example, right? So the limit as x approaches 3 is different than x being 3. So are there any questions about this? Yeah?
Does this sound like similar to like an asymptote almost, where it's like approaching that kind of idea?
Yeah, exactly. And we see later on in chapter 2, the asymptotes that you've looked at, the horizontal and the vertical, we reframe those in terms of a limit. because it's something that you get close to, but you don't actually touch. And so the official definitions of asymptotes do involve limits. So that you've seen asymptotes defined as, well, it's zeros of the denominator that aren't zeros of the numerator, right? Or in the sense of a horizontal, it was like, is the degree of the numerator larger than the degree of the denominator? Are they equal? What are, you know, so you just compared like certain things algebraically defined asymptotes, but really it's a limit process that you're computing. So they just had to find a way around describing asymptotes without using limits until you actually receive the language. So what we've seen here is the nature of limits. The function value can be the same as the limit. The function value might be different than the limit, or we might have a limit when the function value doesn't even exist. So all three of those are scenarios that arise when computing limits. And it depends on what function you're dealing with as to which scenario. But all three of those are perfectly acceptable. And again, it's just illustrating the main differences between function values and limits. Okay. Any other questions about this? Okay, so the idea of a one-sided limit, if you want to go back up here to our first definition, where we defined the limit as x approaches a of f of x equals L, and just maybe somewhere note that this is a two-sided limit. We are going to make a distinction between a one-sided and a two-sided limit. Okay? So the distinction when we're dealing with a one-sided limit, that might not have printed out that well. I know you can probably barely see this superscript above the A. Doesn't look like it printed out all that well in your notes either. But I'll rewrite it. This is limit as x approaches A. And we have this positive, a plus superscript here attached to A. Okay. So that's simply meaning that now it's giving us context as to which direction. If no direction is specified with a superscript, then it's a two-sided limit. Okay. This one here, if you can't see, that's the limit as x approaches A, and the superscript here is a minus on f of x equals L. So the way we would define that here, it's basically the same preliminary definition that we just saw. The only modifier here is for the right-sided limit is that x has to be larger than a. X is to the right of a. So we're approaching from the right. And for the left-sided limit, x is less than a, approaching from only the left. So why would we need a one-sided limit? Why couldn't we just always just use a two-sided limit?
Yeah, there are some times when limit ends at a completely different place on each side.
Okay, right. And what kind of functions are those?
Like tangent or cotangent. Those ones are pretty.
Okay, yeah, like trig functions that have asymptotes.
Any piecewise function where you have a break in the actual function?
Yeah, so piecewise functions. So like, like when you saw these weird functions like this. Remember those? Functions that have restricted domains, like the square root of x function is a good one. So in certain instances, it only makes sense to approach it from one direction, or a value, rather, from one direction, because in fact, that's the only direction you can approach it from, right? Like if I said on the square root function, let x approach 0 from the left, well, there is no function over there. There is no road to travel along on the left side of that. So oftentimes one-sided limits are needed. So let's look at an example of a piecewise function. So let's say we'll have this horizontal piece here at 3. Open circle at x value of 2. That's all one piece. I just kind of left room for the 3 in there. And then we have an open circle above that with this linear part. Here, this y value is 4. And so what if I did ask you to compute the limit as x approaches 2 on f of x? So hopefully, yeah, visually you can see that, well, if I approach from either direction, I'm on separate pieces. Those pieces never actually meet, right? So if it asks you to compute the limit as x approaches 2 on this graph, hopefully your intuition is say, well, that's a two-sided limit, and I can't approach that x value from both sides at the same time because I have two different pieces. So what I have to do on this piece is I then have to look at, well, what is the limit as x approaches 2 from what direction? From the left. I'm coming from the left and approaching 2, an x value of 2 from this side. So I'm going to indicate that in that way. And what is the limit as x approaches 2 from the left on this function?
3.
It's equal to 3. So the y values are getting closer and closer to 3. Again, even though the function's not defined at that location, I'm just saying as I get closer and closer to that, what are the y values getting closer and closer to? Does anyone have any questions about that? Yeah.
So we couldn't go the other way and do as we approach it from the right?
Yeah, so could we even compute a limit as x approaches 2 from the right? Can we do that?
Yeah.
Yeah, except for we have to do what when we look at that limit? Yeah, if I approach 2 from the right, which one of those pieces do I have to use?
Right.
The piece on the top. Yeah, because that's the only way to approach 2 from the right is from here. So if I look at the limit as x approaches 2 from the right, what would that be? 4? What do y'all think? 4? So as we get closer and closer to 2 from the right, the y values are getting closer and closer to 4. Questions? Yeah.
So as x approaches 2, not from the left or right, but from both sides, it would be undefined?
Right. Right. Yeah. So we've yet to make that connection, but if you've read this theorem right here, then it does tie in the one-sided limits to the two-sided limits. So it says that if the limit as x approaches a, if the two-sided limit exists, so if the two-sided limit exists and is equal to L, then what's happening is that we have, and again, I apologize for the type here, but it says the limit as x approaches a from the right is equal to L, and the limit as x approaches a from the left is also equal to L. So in words, what is this theorem saying?
It's online, it's the same.
Do what?
Online, it's the same.
Not necessarily, it doesn't necessarily have to be a line. So let's, that's correct, but let's think about it more broadly.
If your function from both directions is approaching the same number, then the two-sided limit, it's going to be that number.
Right. So it wasn't necessarily a trick question, but the statement if and only if is meant to be read either way. If this is this, then this is this, right? It's not like a conditional statement where you say, if today is Thanksgiving, then it's Thursday. That's meant to be read one way. Like just when you see the if and then, you're supposed to take it in that direction. If you read it the other way around, then it's not true, right? If today is Thursday, then it's Thanksgiving. That's false. Today is not Thanksgiving. But an if and only if statement is, you could read it either way and still have truth to it. So really this theorem is actually saying two things, four things really, if we think about the negation of the statement too. So what it's saying is, one, if the two-sided limit is L, then both one-sided limits are also L. Then we can take that statement and flip it around. So another way to interpret that that's equivalent to what we're saying here, it says if the one-sided limits are both equal to some finite number L, then what we could say is we know what the two-sided limit is. So then the two-sided limit is also L. And again, we get that because it's if and only if statement. We do see some theorems later on where it's just an if-then statement, and you can't look at it both ways. You have to look at it if this, then this happens, and that's it. Okay. So we can also negate those statements and talk about, instead of talking about equality, we can talk about non-equality. So the third thing we could say is that if the two-sided limit does not exist, and maybe we can answer this. If the two-sided limit doesn't exist, what does that mean about the one-sided limits?
They have different values.
Right, good. They have different values. So if the two-sided limit does not exist, then the limit, we'll just write this out, the limit as x approaches a from the right on this function does not equal the limit as x approaches a from the left. Okay, one more. We're going to flip this statement around. And say if the two-sided limits are not equal, the limit as x approaches a from the right does not equal to the limit as x approaching a from the left, then our conclusion is the same. What if the one-sided limits aren't the same, then the two-sided limit does not exist. Does not exist. So looking back at our that piecewise function example, as was mentioned, we would say that that two-sided limit that we were asked initially, what is the limit as x approaches 2 from both sides? What would we say about that?
It doesn't exist.
It doesn't exist because the one-sided limits aren't the same. Kind of ran out of space, but this doesn't exist since the limit as x approaches 2 from the left does not equal the limit as x approaches 2 from the right.
Is that how you want us to answer the question?
Yeah. Yeah. So it all seems pretty simple when we look at the graph, right? If I'm just looking at that graph and I say, what's the limit as x approaches 2? You say it doesn't exist. But the issue is what we'll see in a minute and what we move away from is looking at graphs to answer questions about limits and even looking at tables of values to answer questions about limits. So, you know, the potential, that is how I want you to answer the question, but just as a heads up, if you were given this function, you know, something to the effect of a piecewise function, and then I ask you what is the limit as x approaches 1 on this function, you know, it's highly inefficient to graph that. Especially if you had like 4 questions like that to answer. So this is kind of what we're moving towards being able to do. We're just solidifying our understanding visually so that when we start computing stuff like that, it hopefully makes a little more sense as to what we're actually doing. But yes, that's the answer for the two-sided limit here. Does anyone have any questions about that? Yeah.
So the limit as x approaches 1 from the left exists, but it does not exist for as x approaches 1 from the right?
Okay, for this graph right here, let's look at that. So we're looking at that same graph. And so the question was, what is the limit as x approaches 1 on this function? So would there just be one answer?
Yeah, yeah.
Well,
Yeah,
your x
it would be
one
3.
does not exist.
Okay. Anybody think anything different? Yeah.
Wouldn't it be a two-sided limit because we're only looking at where x approaches 1? And we're not looking to the right? Is
Yeah.
that the answer?
Yeah, look, so yeah, you visualize it here. Here's 1. Can I approach this from both sides? Yeah, there's no issue there. I'm not terminating at that particular location. So in fact, if I ask you to compute the limit as x approaches 1, you would just say it's 3, because we can approach that from both sides on this path. So basically, as long as it's not, say the limit's asking you to approach one of those endpoints, then everything else is a two-sided limit, right? If I ask you what's the limit as x approaches -37 on f of x,
3.
it's still 3, right? Because -37 is way out here somewhere. Let's just say it's there, not to scale, and I can approach that from both sides with no issues. There's no need to look at a one-sided limit. We can look at a one-sided limit, but there's really no point to do so because we can approach from both directions simultaneously here at -37. Any other questions? Okay, figure 2.13. Just take a couple of minutes and answer the question, and think about it, don't just, the graph is a visual aid, but what is the limit as x approaches 2 on g of x? What would you say about that? Depends, right? So who thinks just right now, who thinks it does not exist? Who thinks that limit does not exist? Okay, so you're for sure that it doesn't exist. Everybody else is unsure. Okay, so what do we have to do then to answer this question? It depends on which side you're coming from, right? Which means you have to look at a one-sided limit. So let's start doing that. So what's the limit as x approaches 2 from the right on g of x?
1.
We're approaching 2 from the right. The y values are getting closer and closer to 1. What's the limit as x approaches 2 from the left?
4.
We're approaching 2 from the left, but again, we have to travel on the path. Those y values are getting closer and closer to 4. So then what would we say about the limit as x approaches 2? Does not exist, yeah. Why does it not exist?
Because the left and right limits do not equal.
Okay, because the left limit, the limit from the left and the limit from the right are not equal. So, but again, visually you can see that. It's totally clear that the limit doesn't exist. And the way we see that is the graph isn't connected, right? There's no way for the left and the right limits to exist. Right, not for the limit as we approach, as x approaches 2 from the left. Yeah, so all we're concerned with is as we get closer there, what are the y values getting closer to? Yeah. Yeah. So I mean, they're a little bit weird at first. Just working with them to get the feel for it. I hope it's somewhat straightforward. It doesn't seem like 100% mystical, but you do have to work with it a little bit. Are there any other questions on what we've done so far? If you think of something up prior, then please ask. I don't mind going back.
Or there's a gap in the graph. So like it's like the left side, what if that stops at 1 instead of 2?
Okay, so yeah, like let me see if I understand. So what you're thinking about? What if we had this piece like this? I'll just draw a kind of different, but this quadratic piece came here like this, and did that.
No, like what if they were separated?
Like if one was at like 1, 0, and the other one was at 2, 0 for their ending points. So you just space it out by 1. So say that one on top ends at a
Parabolic,
4,
that
1.
parabolic piece was just shifted over 1 unit.
Yeah.
Shifted over to the left or right?
To the left.
To the left?
Yeah.
So if that piece were right here, like this,
Yeah.
Yeah.
and this piece were here at 2,
Right.
and that's 1, well, what would be the limit as x approaches 2 then? We have different situation, because I can only approach 1 from the left, and I can only approach 2 from the right.
Yeah.
So it wouldn't make sense to say, I mean, you could ask the question, what's the limit as maybe x approaches 1 on this function? Is that kind of what you're thinking? So what if we had this graph and the question was, what is the limit as x approaches 1 on this function?
It does not exist.
It wouldn't exist.
Well,
You can't do a two-sided limit there because you can't approach 1 from 2 sides.
You can't approach 1 from both sides simultaneously, but does that mean the limit doesn't exist? No, because what makes sense to talk about this limit here? Just a one-sided limit. It doesn't even make sense to talk about a two-sided limit here. The reason it makes sense to talk about a two-sided limit here is because these things are lined up at the same x value. And as x approaches 2 from the left or the right, depends on, as we approach 2 from the left or the right, dictates what path we have to choose to do that. Right?
So it's a question that wouldn't be asked.
Right, it's pretty much a question that is not asked, and if it is asked, you have to recognize, like, in the context of this problem, that doesn't make sense, because I can only approach this from one side. So more aptly, you would see this asked of you instead.
That should be a minus.
Oh, right, yeah, sorry, thank you. I don't need to introduce confusion. Yeah, thanks. All right, yeah, all great questions, thanks for asking. Are there any other questions?
So when in doubt, follow the path.
Yeah. If you're computing limits graphically, just follow the path. Okay, so just when you get used to that, and when we say that, we're going to look at another example. These were just extra practice problems I had. We might come back to those if we have time. I'm just going to add this page here. Sorry that I didn't leave you a blank spot to write. But what we're going to look at is try in line of trying to answer this question, why can't we just graph functions to compute the limit? So why can't we just, if I were asked to compute a limit, why not just draw a graph? Or use a table of values. which is essentially giving us the same information that a graph would give us. So we'll answer this question specifically with an example, and then we'll say this is why we can't do this for other types of functions. So just to motivate this, we'll just consider the function consider the function f of x equals to the cosine of 1 over x. And compute the limit as x approaches 0 on that function. So issue 1 hopefully is, well, if x is getting closer and closer to 0, what's happening to 1 over x? Is it getting smaller and smaller or larger and larger? It's getting larger and larger. 1 divided by a super small number is a really large number. Okay, so we might initially think, all right, well, I'm taking the cosine of something that's getting larger and larger. What's the issue with that? Maybe a helpful hint is to think about the graph of cosine. Right, it just keeps doing this. So like even if I'm way out here at 5 billion and then keep going, it doesn't ever actually approach a single value. Okay. The other issue is how do you graph that? It's not easy to graph at all because what we just said, this 1 over x gets really large really fast, and so you're then computing the cosine of all of those values. So instead, let's first take a look at a table of values to see, if anything we can conclude for this limit. So 1, we'll do a table of values. And remember, make sure your calculator is in radians. So we'll do, let's just input 3 different things for now. Let's input 0.001, 0.0001, and 0.00001. Okay, so what is the cosine of 1 over 0.001? Yeah, just leave as many decimals as you can. Zero point 562. All right.
5623.
You want like full
2, 3.
decimals?
And we'll stop there. Okay, how about the cosine of 1 over 0.0001?
Negative 0.9521.
Negative 0.9521.
5563682.
5563682. Okay, cosine of 1 over 0.00001.
Negative 0.9994.
Okay, negative 0.9994. Okay. So if we just said, all right, well, those values are pretty close to 0, what does it look like's happening to the limit? Looks like it's approaching -1, right? Is this getting closer to -1? Oops, that's a question mark. If you want, you can keep computing values. I'm just going to put the table in from your slides here from the textbook. Somewhere. Oh, there it is. So here's some more values that we didn't compute. You may see that. Let's see. So there's some more values. Once we compute with 0.000001, then we see it jumps back up to positive 0.9, then back to negative 0.9, then even worse, jumps up to negative 0.3. So yeah, it's totally all over the place. So the more values you compute that are closer and closer to 0, the less sure that this is actually approaching something definitely, right? Like in our example from 2.1, this was like 49, and then it was 56 or whatever, then it was 69, 63.9, and 63.94, right? And then we could say, well, those things definitely look like they're approaching 64. But these things definitely look like they're not approaching something specific. Yeah.
Can't you approach it from the other side?
Yeah.
The positive side? Like kind of jump up and down.
You can approach, so we could approach 0 through negative 0.001, etc. But you could try that, you'll see the same thing happening. Okay, so this is just a specific example to illustrate why we don't use table of values, because it's inaccurate. So it doesn't approach negative 1. And then we say, all right, well, let's just pretend we could graph it. What would the graph look like? Hopefully we're not making that too much. So then we'll go back to second method or whatever, is graph. It's going to be hard to draw, so if you want to draw it, feel free, but it is going to be in your notes. Oops. This is cosine. So it looks already funky, but we're approaching 0 from either direction. This has only certain capabilities. But let's get relatively close to 0 out here.
Oh, red screen
Just a little
fifth.
bit.
Okay, so close to 0 out here. Can y'all see that?
I can see what you mean by some hard to draw.
It's not gonna work.
Massive
But okay,
block of-
here we're really close to 0. So the oscillations are just becoming more and more rapid towards the origin, which is why it looks like a solid brick right there. So that's not helpful either. And granted, this is a little bit more of an elaborate function than like lines and polynomials and even rational functions, even standard trig functions or inverse trig functions. But it does bring up the issue, like when it's not, the limitations of looking at limits numerically or graphically.
And we're definitely going to be talking about stuff like this, like how to
Yeah.
figure out limits of like cosine.
Yeah, we'll look at some of those more difficult things later on in chapter 2. So just a good example to illustrate why we focus our attention more on the sort of analytic side versus the visual and the numerical side. And by analytic, I just mean working it out by hand and seeing what your answer simplifies to, if anything. Okay, and so that's really the idea. And 2.3 is we start to move away from the visual and numerical interpretations of limits, and then we start to look at them algebraically or analytically. So we need to take a break, and then we need to start 2-3. So these other examples, if you wanna do those and ask me if you got them right, I'll be happy to let you know. But we're gonna skip this just to save time. So we just have those two other graphs to look at, but we're gonna call it good. All right. Let's take a 10-minute break, and then we'll start 2-3.
Are there notes that we can put for 2-3?
Yes, there is. Yeah.
You'll be good. It takes a minute to get used to it.
Kind of makes sense.
That's better than just.
I guess probably what really helps is like, basically when I touch, I'm about to apply the whiteboard right before I touch it. That's I was like, okay, sure.
You say
Visual representation.
All over by our weather.
Conclusion. This black one and this green one are the two fine points.
You're right, we gotta get it cool.
Yeah.
If you want to get something at
No,
sea,
sorry,
say
all
it now.
Right?
I like the colored ones.
Yeah, they're very
Those are like thick.
You like my aqua notes
Cute.
of exclusively cool tone colors.
Really?
I got this in it and I'm see, these ones are great.
Yeah, but like these two are two fine points.
Now we're gonna
While I don't have this dress,
Yeah,
I'm gonna do that thing. That's it.
However,
What is it?
but I still have my tried and true.
I got these in this one.
However, this was a great purchase.
Wait, you took
Yeah.
the place
Yeah,
test?
worth
and
it.
just put you in the-
Worth buying an entire pack for just that color.
They said I got a really good spot.
Right? Try this bad boy.
Ooh.
I like that color.
I'm gonna study.
I'm just
I
saying.
like practice math. Because I'm gonna fail. I'd rather just not have the test and fail it.
Or pay for it and then they're like towards the end get it done.
That's good. Yeah. It's better that way, huh?
And those.
You pay for it and you're like.
Oh,
No, it's not bad. It's like different than
shiny.
I can get a refund. But I
That's
think
because this one's the gold.
I'm sure there's like really good skills.
And my daughter's got me a bag of 12 of these in all sorts of, and I'm like, at first I was like, wow, I feel like a 12-year-old girl.
Yeah.
But turns out,
I will
photo
video.
notes is, oh my God, like it's like drawing a
you guys
picture.
all like
So it visually stays in your brain.
They can do math
Like
really well.
12-year-old girls know what that
Well, I think that's the same brand as my pencil.
Oh.
is. Yeah.
Okay, I was like.
That everyone thinks is.
Yeah. What? Nah, but I didn't do math for my senior year.
But I love this pencil.
I didn't even take
That's why I was freaking out
So I
on Monday. I
was
was like,
like,
or Tuesday. Well, you
what
find
is
it.
this?
In a plastic bag with a t-shirt in it.
Oh, all right. Good place.
Yeah.
Good place.
Where it belongs.
I took Calc 1 and Calc 2.
Like no idea why it was there. I think it like I might have been trying to tidy up, and I just like
I don't know
tossed
if
things
it's
in.
right,
Yeah.
Yeah, or if I'm like cleaning out my car, I'll just like everything into something I can carry. And then find it like 6 months later.
Yeah. I'm glad I found it though, because this wasn't.
Yep.
I don't know. This has been my tried and true.
This all makes sense.
And then I love these pens. Like I find it hard to find a different pen I want.
I know, they're nice. I used to buy them
She
in packs of
graduated
40
legacy.
for serving. I saw like them floating around my house, but we weren't allowed to use them. Like, they're all black.
I use a purple pen at work. Yeah.
Okay, fingers crossed, 'cause I got.
I was in our house, so there was really specific, like, one time this girl, she only used like pink and orange, and then one night the manager was like, no, we've told you so many times that, like, we're not gonna take any of your credit card receipt tips, because you didn't sign them in the right color, because they've been telling us.
That's what I'm trying to get my homework done.
Yeah, I know.
I'm crying.
Like, in our handbook, but isn't that ridiculous? I've never seen someone respond so much. Work at a restaurant, no way. I do, quickly, yeah, I write in purple all the time. I am a purple writer.
But it's better to like do it.
I don't know. It's not the same as like working at like a real restaurant though. I mean, we are a real restaurant. We serve fresh food, whatever. But like, it's not like a store. Yeah. I understand what you mean.
Yeah.
Once we finish it, then finish it.
That's what I tried to, but their servers are down. So I was like, oh, I only got 2 problems in.
I actually called my GM out and he lied straight to my face instead of saying that I was right about something. And I was like, bro, it's not even something worth like arguing about, but I know I'm right.
It's a bunch of little hicklers, right? And the problem is, the jobs are not worth fighting. So people are happy to just be like, okay, whatever, dude. I will just put up with this shit for the next 3 days until I can get another job.
Yeah, exactly.
And sadly, there's basically no incentive.
No, there's not. I really went to high school. I mean, the reason why I got it out is because I lost out on $150. I got screwed out of because of him. And when I called him out, he tried to lie to me. And I was like, no, actually. Because our houses take reservations, especially for big groups. And so he had a 40 cup, and they never complied. So he shut my section down for 2 hours, so that's like $200 that I lost already. And then they never showed up. And so I went up to him and I was like, hey, listen, you're not supposed to shut down sections. We're not supposed to take parties, and like I'm supposed to be just taking people. And also, if it's a big party, they'd close my hours like an hour ahead of time, not like 2 hours when I came in here. And he was like, actually, we do take reservations. I was like, really? Because I was here when they changed the policy and we stopped taking reservations 2.5 years ago. And it just straight up lied to me in front of everyone else when I quit. So I was like, screw you. I was like, you don't care about me, like, working here.
The servers are not paid.
I'm not
criminals.
On top of everything.
Right?
But
It should just be like Europe where tipping is optional and we get paid hourly.
yeah, back in the 1920s, tipping was considered
not my forte, and so they
desperately undemocratic. It's like, you swine, you dare try to bribe me when everybody in this restaurant is the same?
College algebra. It was, what I read was that tipping originated from like a lot of racism because they used bartender in the 80s, paid them under minimum wage, right, which is where that. And I'm sure like, at that time it probably helped out, but now that everything's like equal pay, I mean,
Not only do you get paid minimum wage,
the rest of my siblings were all from college algebra. Yeah. They're like, I don't know what's going on. Barely made it out with C. They're
on
like,
top of it,
yeah,
it's really for a job. Because the people eating felt, you know, felt necessary, or no, it's like, no, you kicked ass, here you go. And it's all right to say you kicked ass, here's $1.
right.
Because you're still making, you know, 11 or 12.
no one wants to do lollipop.
It's like the chili
I mean, up or down. I could go both ways. But if I'm not as stressed about like rushing a table out, I'm gonna spend time with them and let them chat instead of having this system where like I want to get you out of my table because I want another table. Or if I have a large party, if it's there for 5 hours, they're staying there for 5 hours, having a lady game, then I'm kind of like, great, because I can work that out. That's the other thing that made me really mad is when I was there,
I was like, I'm still taking out money I can use. And I was like, that's wrong. But they don't care.
That's literally.
I know, and that's, yeah, exactly, and that's why I was like, that is wrong. For you to have that. So, because they do it automatically, so whether I actually make a 20% use or not, 5% off gets taken out, so when I get injected, it's like, people, I didn't know you. Isn't that sick? Yeah. Actually, I have a fracture in my wrist that's gotten really bad from surgery. And that they didn't care about, and I told them that like my wrist was fractured and I need some time off, and they were like, well, you don't have a cast on, so, yeah. If I intercept with myself now, it's my own fault. It's just the risk that I'm seeing.
I actually like to see, and this is my social structure. I would really like to see reviews come back, especially in industries where the most vulnerable people tend, and where even like even if they're taking like, you know,
Oh, yeah.
5%
I buy those all the time.
that's not enough to fall under the
That's not a
if you're making it too much than it would be for someone else.
We're talking about the techniques to compute limits. So this is where we, again, move away from graphs and tables of values. Maybe I should just use the notes that you already have. Techniques for computing limits. There's a couple of functions that we're familiar with already that we look through here. We're going to look at, in this order, linear functions, polynomials, rational functions, do y'all remember rational functions? What is, like, give me an example of a rational function.
1 over x.
1 over x. Do you remember those weird things? You know, those types of things where we take the quotient of two polynomials, one polynomial divided by another, and we look at some other types of functions. So other. The first two are really straightforward in the sense of a limit. So like the limit of a linear function, we have AB and M being any real number, and a linear function f of x is mx plus b. When we compute the limit as x approaches a on f of x, as long as it is a linear function, that's the same thing as evaluating the function at a. So remember before we just said, you know, depending on the function, evaluating the function isn't the same as computing the limit at a. But for linear functions, we're saying that it is the same thing. And if you have that graph there, you know, I think visually, you know, we're looking at this visually to sort of solidify that, but it is stated in this theorem without proof. When we look at a linear function, it doesn't have anything crazy going on like breaks or jumps or like, you know, oscillations towards the origin, right? They're just nice, simple functions. So for any linear function, I can approach something from either side simultaneously. So in fact, finding the limit on a linear function and evaluating the function there at that location is the same thing. So when we're able to just take this limit as x approaches a and to evaluate, all we have to do is plug it into the function. We're going to refer to that as direct substitution. We're just directly plugging that a into the function. So I'll just write this here. Limits on linear functions are evaluated by direct substitution. Direct substitution. Here's a example. If I ask you to compute the limit as x approaches 3 from the left on the function 2x plus 1, what is the limit there?
7.
7? Do y'all agree? So notice the theorem says something about the two-sided limit, and the previous theorem tied two-sided limits to one-sided limits. So it's not explicitly stated here, but implied in this is that the one-sided limits are also the same thing as f of a. That's the only way that two-sided limit is equal to f of a. So if you want, just so you're clear as to the implications of this, it's also a built-in statement about the one-sided limits. So all of that stuff's equal to just plugging a into the function. And in 2.6, we sort of look at the technical reason, like when we're able to do that. But for now, we're just going to look at certain functions where we can do that, and we'll see other functions where we can't do that. So don't forget that, here's another example. Don't forget that constant functions, like the limit as x approaches -2 on the function 7, what would that limit be? 7. So don't forget, constant functions are also linear functions. So that linear function, f of x equals 7, is just that horizontal line. It doesn't matter what you approach. The y values always approach 7. Sorry, I realize I kind of skipped this here. Just color code this. All right. Questions on that? Straightforward enough. So just think about this section. A lot of these things we look at, we're sort of, taking these baby steps towards wrapping our heads around how to compute limits. So, maybe like if we didn't know any of this, we would say, well, how do we compute a limit? Let's start out with the most basic function we know, which is constant functions and linear functions, and see what happens. And then move our attention to other more complicated functions. So we started off with linear functions. We say, all right, well, that seems pretty legitimate and doable. But if we then wanted to turn our attention to polynomials and say, well, what if I compute the limit on like x squared plus 3x plus 5, right? Well, then we have sums and differences and powers to contend with once we start computing those limits. Okay. So then we might start investigating, well, what happens when I compute the limit on like x plus 2 or 2x plus 3? Is it the same thing as computing the limit or distributing the limit across addition and subtraction? Same thing with powers, etc. Why is this blank? Is y'all's blank? No. Sometimes it just pulls up blank stuff and I don't know why. So then we say, well, are there laws that we can look at in certain ways that limits behave? And that's what all of this stuff tells us.
Oh, God.
So it looks overwhelming, but in practice, I hope that it's pretty straightforward and intuitive. So we're looking at two different functions, f and g, and assuming that their limits exist. And then we look at, well, what happens if I take one function plus another function? So what this theorem is saying that is if I've got the sum of two functions and I'm computing the limit of that, essentially think about it as I can distribute that limit operation across the sum and I can distribute it across the difference. So here, 1 and 2, we'll look at some examples of that. So for 1 and 2, for instance, let's compute the limit as x approaches 2. And yeah, I guess it's kind of hard to do this without powers and stuff just yet. So what kind of things could we do here? I don't know. Let's just say we had 2x minus 5x plus x, and we had to compute the limit there. Probably wouldn't see that because algebraically you would just combine like terms, but we're just going to illustrate this limit law, and it just says that we can compute the limits individually, basically distributing this limit as x approaches 2 across the sums and differences. Eventually, once you do a few of these, you'll get to the point where you're not really writing that out. You're just kind of computing it all at once. I don't expect you to write all of these limit laws out every time you compute a limit. It would take up way too much time and space. But we're just familiarizing ourselves with what can we actually do with that operation. Okay. So anyone have any questions on that? Yeah.
Not necessarily on the thing itself, but
Okay.
because it's not showing up on the website or T2L, are you going to just like try to re-upload it? Because I just want to visualize those laws.
Okay. Yeah, I'll upload this for sure.
Okay.
Yeah. Yeah, I don't know. For some reason, like when I have notes and I upload them, like it just randomly deletes a page or two.
I'm just not a visual person, so.
Yeah, so that's the sum and difference laws. I mean, it's really the same thing because difference is just addition of the opposite. 3 deals with constant multiples. So if we have a constant multiple times a function of x, again, we can just think about the limit as x approaches. That's just operating on things that involve an x. Okay, so if I have the limit as x approaches -1 on like 2 times x. We've already talked about 2x is a linear function, so we would just plug -1 into that and evaluate the limit. But I could say that it's the same thing as 2 times the limit as x approaches -1 on just x, and then multiply those together. So that's what the constant multiple rule is telling us. The product of 2 functions, again, the limit operation can be distributed across products as well. So I don't have space for that. I'll write it down here. Okay, right now we're sort of limited in what functions we use, but say we had the limit of 2x times 3x, for instance. Again, more than likely we would just multiply that out, but so we can say that's the limit as x approaches 1 of 2x times the limit as x approaches 1 on 3x. Okay.
I have a quick question.
Sure.
For the constant, so are you, since the 2's out in front of the limit, is it basically just multiplying 2 times 1 then if the limit's 1?
Yes,
Okay.
right, exactly. Yeah, and so, you know, the constants hopefully are easy to recognize because they're just a number times a function of x, however elaborate that function of x is. So yeah, we could continue and write this, well, that's 2 constant times a function of x. I could even pull that out front if I wanted to. So I have 2 times the limit as x approaches 1 times 3 times the limit as x approaches 1 of x. x. And again, most of you probably won't write it all out like that, but it can be helpful to compute limits, at least initially, I think. So, whatever makes sense to you. Okay. We have a similar situation with the quotient rule. Again, a quotient is related to the product. It's just multiplication by the reciprocal. So the product and the quotient rule are basically the same rule, but explicitly the limit gets distributed to the numerator and denominator. Is that clear, or is it confusing? It might be confusing if you look at just the generic notation.
Is this trying to kind of helping us with just polynomial limits?
Well, so yeah, so what this is building up to, some different constant multiples, products, and powers. So 1, 2, 3, 4, and 6. That those put together deal with polynomials. When we look at the quotient, then we have kind of like the polynomials and the rationals. Okay, because the rational functions, you would have a polynomial up top and a polynomial on bottom. So this is kind of what all of these are building up to, initially anyways.
So essentially, we'll be able to look at the question, know what rules we need to use to solve the problem.
Right, yeah, depending on what operations are present, sum, difference, product, whatever. So the limit as x approaches 0 of 2x plus 1 over 3x minus 1. We could say that to compute that limit, it's equivalent to taking the limit as x goes to 0 of the numerator and dividing that by the same limit on the denominator. And then so we can look at that, well, the numerator is just the limit of a linear function plugged directly in. Denominator, limit of a linear function, I can plug that in. We'll look at more limits. It's just writing these examples to get us familiar with these properties or laws. All right, the power rule for limits, what does that say we can do? Right, so it's saying that if I've got a function that's a function of x that's raised to a power, that I can just pass the limit through and then compute the power after I compute the limit. So like, what's the limit as x approaches 1 on, I don't know, x to the 4th? I can rewrite that as the limit as x approaches 1 of x, and then instead of raising x to the 4th, compute the limit first and then raise all of it to the 4th. Again, just think about limits here like this in this notation. They're only affecting the things that have x. The power is sort of like a secondary thing. And then our root limit law, we've got, let's see, n is even. So this is explicitly talking about even roots. So it's kind of the similar thing with the power, except for we have that stipulation, as we always do with even roots, is that you can't have a negative underneath an even root. So that's what this is, provided f of x is positive. I mean, that's, again, equivalent to the power rule with sort of the caveat that we already know, that I can't take the even root of a negative number. So, you would see that in practice, like if I said, what's the limit as x approaches -4 on the square root of x? Even if we attempted to pass that limit through the root or the power, it's really just a power, right? What we end up with is this. So you just can't do that. So I think at that point it becomes obvious that that's not going to evaluate to something real. Okay. Do you have any questions on any of that? All right, so just a few examples. And maybe like the first few I'll write out in terms of the limit law, but again, I don't expect you to do that by the time the test rolls around. Okay. So maybe you already have computed this limit in your head, but what you're actually doing is, we see we've got the limit of a function of x that involves a few things: addition, subtraction, there's multiplication by constants, and there's powers involved. So rewriting this, we're first going to distribute that limit across the sums and differences. Okay. The last two terms are basically boiled down as far as they can be boiled down. This first one here, we still have to deal with the constant multiple and the power. So just one more step here, we're going to pull the constant out. 2 multiplied by the limit as x approaches 1 on x squared. And then the other 2 we could compute at this point. What can we do with the limit as x approaches 1 on x squared? You can square all of it, so we're going to just scoot that square out. Compute the limit first, and then square that.
Can you square the 2 as well, or should we just?
No, don't square the 2, because it's just 2 times that function of x. So is everyone clear that we wouldn't square the 2? Like, it gets pulled out first, and then we're just passing that limit through the power on x. Any questions about that? So then what these laws help us get back to is something that we already know. Here's the limit on a linear function x, here's the limit on another linear function x, and here's the limit on another linear function. So now that I'm looking at just linear functions, I can say, well, all I have to do is plug 1 directly into x here, plug 1 directly into x there, and then that last limit is just 2. So it's like it's a very tedious process to sort of boil certain functions down to just linear components, but that's basically what we've done with these limit laws. So the limit as x approaches 1 of x is just 1. So let's write this here. It's 2 times 1. We have plus this limit again, which is just 1, minus this limit, which is 2. So we have all of that equaling 1, and that's our limit. Just an illustration of those laws again. What happens if I just, from the very beginning, directly substitute 1 into that function? Get the same thing, right? So if I just take this value that x is approaching, and just plug that in, I get the same result. So really we didn't justify or prove, but we've seen with this example, and if we looked at more, we might suspect that, okay, well, for any polynomial I'm dealing with, I can always boil that polynomial down to just a limit on a linear function. Therefore, with polynomial functions, I can always just directly substitute into those as well. And so that's kind of the whole point. So maybe, I don't know, maybe look at one more. If you were asked to compute the limit as x approaches 0 on 3x to the 4th minus x cubed plus 2x squared minus x plus 4. for this is a polynomial. Instead of breaking this down with all of those limit laws, I'm just going to take that value that x is approaching and plug it into my function for x. To get 4.
Now for like a test, if we just jump to the last step, is it, even though you say evaluate, do you still want us to write down the whole thing, like each step? Or is it okay if we just write the last step?
Yeah, this is what we just have written down here with this 0 there. That's totally fine. And honestly, the ones on the test will probably be a little bit more involved. Because, you know, once you've done a few of these, you see that it's straightforward. It's just equivalent to plugging the value into the function. But like we saw in 2.1, that's, or 2.2 rather, that's not always the case, right? The function value at this location, whatever we're approaching, is not always the same as the limit. But what we're saying is if we're dealing with linear functions and polynomial functions, that it is the same. So let's just write that polynomial functions, rather limits on polynomial functions. Limits on polynomial functions are evaluated again by direct substitution. And so that's also implying the one-sided limits are evaluated the same way. So the limit as x approaches 4 from the right on the function 3x squared plus x minus 1. Just a lot of this stuff is function recognition, like what kind of function am I dealing with? Usually dictates like what process you take in order to compute the limit. So I see, well, that's a polynomial. I can just plug that value directly in to compute the limit. Okay, so that's how we compute those limits. Whether they're one-sided or two-sided, on polynomials and linear functions, we just plug directly into the function. Yeah.
So if you have a limit, like let's say it was approaching from the left, would it be computed the same way, or would you have to include the negative sign as well?
Yeah, we would compute it the same way. So if this were the limit as x approaches 4 from the left, you mean? Mm-hmm. Yeah. If 4 from the right or the left, wouldn't matter. You just plug the 4 in. Yeah, so true for linear and polynomials. Because again, if you think about the graph of a polynomial function, like, you know, however complex it is, it's still all together, right? So no matter where you are or what you approach on a polynomial, you can always approach it from both sides. The one-sided limits will always be the two-sided limit. That's not what that function looks like, but just to give you a visual. All right. Any other questions?
So then would that be 51?
Do what?
Does that have to answer 51? For the limit, so x is x approaches 4.
Oh, is x, so what about it?
So what's the final answer?
I don't know,
It equals
16.
51.
I got 51.
Okay, yeah, 16
Okay.
times 3 minus 4.
Just making sure.
38.
48 plus 4 minus 1.
Oh, I already had that there, my bad. Well, now you see it twice, it's important. It could save you a lot of time. Let me see what's next. Okay. So let's look at now polynomial or rational functions, which are the quotient of polynomial functions. So we're just going to take for a fact, we didn't see the theorem, but we're going to accept it moving forward that when we're dealing with polynomials, we can also just directly plug into. The issue when we start dividing things is what? We've got to be careful that we're not dividing by 0. Okay? So here's the general strategy for any limit you ever see. The first thing you want to do is just start out by plugging this thing in. If you get something weird like division by 0 or the square even root of a negative number, stuff like that, then that's when you pause and say, okay, let me try to figure this out and see what's happening. Okay? But we always want to start off by just plugging this in, because if and when we can plug this directly in, then you're done. You have the specific value of that limit. All right? So we're going to compute this. We'll just throw 1 into all of this and see what happens. Well, clearly we're not going to divide by 0, so we can just evaluate this. So what do we get?
1/5.
So that's it. That's your limit. Easy enough? Yeah.
Could we possibly factor the top one and cancel out?
Yeah. You could try to factor that, but since it worked, I wouldn't try to factor it. It worked, you're done. But in the same vein, when we get to example number 2, we try to plug 2 into this, and then we're now dividing by 0. Right? So let's just go ahead and write this out. We'll go ahead and put this in. Because whether you're doing it in your head or on paper, you're still going to get to the point with certain examples where you're doing something you're not supposed to be doing. So then that begs the question, is that a limit that doesn't exist?
That'd be approaching somewhere.
Okay, so let's ask this question then. If I approach a finite number, let's say 2, on any function, does it always have to approach something? What happens if we've seen what happens if we approach like a finite number on a linear or a polynomial? We always get some number in return. But like if I approached 2, couldn't the function just keep going off to infinity? Could, right? In light of 2, it could also be that we have a hole, or yeah, we'll just call it a hole right now, right? It could be that there's a hole in that graph, which we know that just because there's a hole there, yeah, the function doesn't exist there, but does the limit? Yeah, the limit still exists even if the function still has a hole in it. So that's what we've got to figure out. Is this a limit that does not exist? Or is it a limit that actually exists? So what we'll do now is we'll factor this and just work this algebraically. So we have x minus 2 times x plus 2 on top over x minus 2. And then we can see what happens here algebraically. These factors are gone. And then we're just computing the limit as x approaches 2 on the function x plus 2, which is 4.
For this example, x was approaching -2.
So if if x were approaching -2, then it would be 0 over -4, which is 0. Yeah.
So it's okay to divide 0, not divide by 0. Yes.
Yeah, right. So you can have a 0 upstairs, so you just wouldn't have an upstairs to your house. If you're living under nothing, you got problems. So does this look familiar when we say, well, here's this function, let me factor it, then, oh, hey, this thing crosses out, right? That was like super common when you were dealing with rational functions. Without the context of a limit, anytime a factor in the numerator and denominator crossed out in a rational function, that meant you're sort of getting rid of your vertical asymptote and turning it into what? Oh, what? A whole. So do you remember that process? Whenever I cross out a factor, x equals 2 is a whole, because the factor x minus 2 was canceled out. It's the same exact thing here. The reason we're able to cross this factor out, and it was never probably explicitly stated to you in pre-calc, because you can't really talk about it without the terminology of limits. But are we crossing out 0 over 0 here? You'd say yes? That's very reasonable to say yeah, because x is approaching 2, right? And we're crossing out x minus 2 over x minus 2. But it's a limit. It's saying that as x gets closer and closer to 2, what does this thing in green get closer and closer to? It just gets closer and closer to 0 divided by 0. It's not ever actually 0 divided by 0. So that's why we're able to cross that out. If it's 0 over 0, you can't say 0 over 0 is 1. It's only because we have this limit here that this is like 0.0001 divided by 0.0001, and so on and so on and so on. It's never actually 0 over 0. So what does that mean? As x approaches 2 on x squared minus 4 over x minus 2, the y values approach 4. In terms of the graph, we've already stated that means there's a hole in the graph. Okay. So that's summarized here. For any limit you compute, whether it's a rational function or some crazy trig function or whatever, if your function is undefined at x equals to a, and if a is finite, and you compute the limit as x approaches a on that function and get some finite number in, then what that means is you've got a hole in the graph at a comma n.
So we just take what we reduced and like you said, equal to y. Kind of like
Yeah.
pre-calculus.
Right, exactly. The only issue with graphing these things, as you probably know, when we graph this, it looks like a line because, in fact, it's simplified to a line. It is equivalent. This function here is equivalent to x plus 2, but this is as long as we graph x plus 2 with a hole in it, they're the same function. You wouldn't necessarily see that. Look, you wouldn't necessarily see that. Like if I just said, all right, we'll have this thing graph x plus 2, we see the exact same graph, but we know it's not really x plus 2. It came from x squared minus 4 over x minus 2. And through that process of analysis or through algebra, we see what's actually built into that is one of the factors gets simplified, and just like when you simplify anything, you always lose a bit of information about the thing you started with, right? So if we just said, hey, it's x plus 2, you're wrong. It's not x plus 2. It is everywhere except at the hole, which was at 2, 4. And that's sort of like a pre-calculus approach you would have taken. You would have said, all right, well, I want to graph this function. I'm going to graph x plus 2. But I know this factor dropped out. I have a hole when x is equal to 2. But, where is that? I have to then find the y value. The y value, I can't plug this 2 back into here, so I had to use the reduced equation. When I plug 2 into that for x, I get a y value of 4. So over here at 2, 4, I have this hole, and then I just put that in my graph. So it might have been a while since you had pre-calc or algebra, but, you know, hopefully that is somewhat familiar. And without thinking about any of that, we should get accustomed to, when I compute this limit, the original function is undefined at 2, but what I'm getting out is a finite number in return, which means I have a hole in the graph. And that's always the case. So that's what this statement is saying. If you approach a finite number that your function's not defined at, but you still get a limit in return, then you have a hole at a comma L. You know, maybe we should change this to L to keep it with our notation or definition, but it doesn't really matter what we call it. Again, it's you know, when you graph these things, you don't see the holes, which is why you have to analyze it. I mean, we could take this function and just chug along here and say everything looks fine, right? Oh, until we get right there. Then it shows us that it's 2 comma undefined. But where is that deleted point? It's here at a y value of 4. Okay, so just, you know, moving forward, a lot of these functions that these limits that we deal with, if you can remember like stuff from pre-calc or algebra, they tie in perfectly. It's just now that we're putting the context of a limit onto it, it does look a little bit different, but it is the same thing. Questions? Okay, another type, not necessarily a rational function because we have radicals involved. And we'll see that there's 2 methods that we could use to evaluate this. The first method is the conjugate. Does anyone remember what the conjugate is? Like, I'll erase this, but if I said, I don't know, 1 plus the square root of 2, what's the conjugate?
1 minus 2.
1 minus the square root of 2. Do you remember that term? It's basically whatever you have, the conjugate of that is to get you basically to multiply the difference of squares. And so why would that be helpful when you're using radicals? Yeah, you get rid of the square root whenever you square either one, right? If either one of those were a radical, then you would just get rid of the radical because you're squaring both of them. Okay, so that's the idea of a conjugate and kind of how it helps us with functions that involve radicals. But we know since we're dealing with a quotient here that you have to not only involve the conjugate on top, but on the bottom as well. So we're basically taking a fancy form of 1 and multiplying this function by it, just to see if it looks different, right? So let me get rid of all that stuff. But again, you know, we should start out by saying, well, what happens if I just plug 1 into this? So we get that weird thing 0 over 0 again. We saw in the last example 0 over 0 was, in the sense of that limit, was actually equal to 4. Let's see what it is here. So the conjugate, maybe specifically of the thing that has the radical, the conjugate of this right here, is what? Square root of x plus 1. Remember, the whole thing is a minus b, a plus b. Those are conjugates of each other. So what I'm going to do is take this limit as x approaches 1, the square root of x minus 1 over x minus 1. And I'm not changing the function. That's really important. Don't change the function that you're computing the limit on, otherwise you just invented a new limit problem that you weren't given, right? So I'm just going to multiply this by a form of 1 that involves its conjugate, root x plus 1 over root x plus 1. That way I'm not changing the function, I'm just changing the way it looks or changing the way that it's represented. And then I just have to actually multiply all this stuff out. So I could either use, I could either kind of take this algebra right here off to the side and then write one more limit statement, or I could just simplify as I go, writing the limit, the whole way down. There's really not a convention, but what I see a lot of is that you're computing this limit, so like on the exam, people just totally drop that notation and just start working with the function itself. And then, at the end they say, like 2x plus 1 is equal to 5. Is that true? No. So you end without a limit, without that, 2x plus 1 doesn't equal 5. So when people write stuff like that on the test without the limit, I try not to be picky about that, but I should be, and you should be very conscious of your notation and not drop whatever operation you're performing. So try not to do that. If you don't want to, if it's fine if you don't want to keep writing limit as x approaches 1, limit as x approaches 1, right? If you don't want to do that, then just take your algebra stuff off to the side and simplify that, and then come write it in later with the limit. So let's just simplify that. All right. So what does what the numerator turn into? X minus 1? What do y'all think?
Yep.
Okay. What about the bottom?
X minus 1 times root x plus 1.
What was it? Is that what you said?
Yeah.
All right.
I mean,
Now-
before you even go that far, you just.
Right, yeah, and that's the point that I wanted to bring up. The issue with computing this limit, and this will always be the case no matter what kind of function you're dealing with, the issue with computing this limit was the fact that we were dividing by 0 here, right? The thing that caused us to divide by 0 was this factor here. We just happen to have the only factor here in the bottom. But if we had like 12 factors in the bottom, we want to focus on the thing that's causing us to divide by 0, and we want to leave that thing as it is. Because otherwise, if I write it like this instead of like this, where I'm not really going to multiply out the bottom, I'm just going to represent it as a multiplication. If we write it like this, as opposed to like expanding everything out on the bottom here, it's a lot more clear as to what's happening, right? What's happening is these two factors are just going away. But if I have it written like this, I don't see that cancellation taking place. So the fact of the matter is when you're simplifying limit stuff, the problem or the thing that's causing you to divide by 0 in the bottom, just leave it alone. Don't multiply it through into anything else. Just leave it there as is. So we don't even want to go that far in multiplying the bottom out. I'm going to rewrite this, but we want to simplify it that way instead.
So don't be afraid to write things along with things here.
Yeah. Generally, the numerators you multiply out fully. The denominators, whatever factor is causing you to divide by 0, just leave it alone. Which usually equates to not multiplying things out in the bottom. So we simplify that, and we end up with just 1 over root x plus 1.
You have to rationalize the denominator.
No, we don't need to rationalize the denominator at this point because the issue was the division by this factor right here, right? That was causing us to divide by 0. But through this process, we've now eliminated that, and we don't have that issue anymore. Does that make sense? Yeah, so then what we'll say is that I've simplified that. Make sure you come back here and say, that means this limit as x approaches 1 on the original function is equivalent to the limit as x approaches 1 on our simplified function. And then what is this limit?
Does that mean there's a hole at x minus 1?
Okay, right. But the limit is 1 over the square root of 1 plus 1, which is 1 over 2. So right, that's exactly right. Notice we have this function that we're approaching 1, but the original function is undefined at x equals to 1, right? Because it caused us to divide by 0. So I'm approaching a number that my function is undefined at, but I'm getting a number in return as the limit, which means that this function has a hole where?
1, 1/2.
Yeah. Remember, the limit is always your y value. Does anyone have any questions? Yeah.
Can you kind of repeat to me why there is a hole at 1/2?
Okay, so the reason there's a hole, just think about it this way. When a function's undefined, what do you have? You either have a
Asymptote or a hole.
a vertical asymptote or a hole, right? Like those are the only two ways to represent somewhere where your function's undefined. Okay, so with that in mind, x is getting closer and closer to 1, and y is getting closer and closer to 1/2. But we know the function's not defined at 1 because it caused us to divide by 0, right? And we know since we ended up with a finite number as the limit, this place that it's undefined is not an asymptote. If it were a vertical asymptote, what would happen to the limit?
Infinite or negative.
Right. So when you get closer and closer to a vertical asymptote, your function starts to do that, right? So when you approach a vertical asymptote, your function values just keep getting larger and larger. It's only when we have a hole where our function values approach something finite. So I don't know, I hope that helps, but
Yeah, I get it.
it is something we need to consider because in 2.5 and in 2.4 and 2.5, we do start to look at those types of limits. So it is something we need to start thinking about so we can kind of keep it straight once we get there.
Is the numerator always going to be equal to what the domain can't equal?
Not always. Like if it were like x, if it were like the square root of x plus 1, square root of x minus 2 instead, then we have to have another way to compute that because those factors in the top and bottom won't cancel out. And in fact, when we get to chapter 4.7, we'll look at other ways to evaluate limits when we get like a 0 over 0 situation. Okay, method 2, this method doesn't always work, but we could take the denominator, which was x minus 1, and we could factor that. Was that minus 1? We could take the denominator x minus 1 and factor that. We're not really used to factoring it because, in the sense of polynomials, linear factors are like prime numbers. You really don't hardly ever break those down anymore. The first method with the conjugate with these types of problems will always work. If you can recognize you can factor, it is more efficient, but it's not necessary that you recognize you can do that. And I think maybe once you see one or two of these, it starts to become obvious, but it's not obvious at first. I'm going to factor x minus 1 and pretend that x minus 1 is a difference of squares. So I'm going to call that square root of x minus 1 times the square root of x plus 1. Can I factor x minus 1 that way? Yeah, if you're not sure, just FOIL this out, right? Expand, we have root x times root x times 1, negative 1 times root x, and negative 1 times positive 1. So these two things are 0, and we have x minus 1. So then we can see immediately what happens. Those two factors divide away, and we're looking at the exact same simplified function that we looked at above. Any questions? There's the graph of our function, but we know that as I approach 1, that this y value here is a half, and the function's undefined there. So still a lot of like pre-calc stuff is super helpful here. Oh, that's 1/2 right there. Sorry, I should have scrolled down more. There's one. There's 1/2. Okay. So there is like a pre-calculus review on MML if you need to refresh any of those things. It's definitely worthwhile because it helps out a whole lot with limits for sure. See y'all. Have a good weekend.
Yes, absolutely. So, unfortunately.